Hello, everybody. This will be our final lesson for Chapter 4, Newton's second law. This is on falling and air resistance, which is non-free fall. So it is non-free fall when it is normal falling, and it is free fall when it is only gravity and no air resistance. So this is going to be normal, non-free fall, which is normal falling. All right. We're going to be working through this practice page to help clarify that concept for you and how terminal velocity works and how surface area affects air resistance. So, to start off with, we want to read the setup for the question. Bronco skydives and parachutes from a stationary helicopter. Various stages of fall are shown in positions A through F. So you're going to be figuring out the acceleration of Bronco at each position. Letting downward be positive in direction and using Newton's second law, acceleration is equal to net force over mass, which is equal to weight minus air resistance over mass. Find Bronco's acceleration at each position. Answer in the blanks to the right. You need to know that Bronco's mass M is 100 kilograms, so his weight is a constant 1,000 newtons. Air resistance R varies with speed and cross-sectional area as shown. So to just start off with, we have this equation given to us. Acceleration is equal to net force over mass. So we already know Newton's second law is F equals M times A. So force equals mass times acceleration. More specifically, force is the net force. And so for any particular situation, to know if the object is actually accelerating, we need to know if there's a net force. So force often has subscripts, as we discussed yesterday: net force, force of gravity, weight, normal force, force x direction, force y direction, etc. We're going to be dealing with two specific types of forces today. One is W, that's referring to his weight, and R is referring to the air resistance force. So the force that the air is pushing up on him as he's falling. And those are specified with the letters W and R in this example. So if we take a look at the first picture, he is leaving the helicopter. His weight is listed as 1,000 newtons, and R, which is air resistance, is listed as 0. So this means he has not yet started falling. This is the instant split second right before he starts falling. I'm going to start by showing you how the weight calculation is done. So in the question, we're told that mass is 100 kilograms and that his weight is 1,000 newtons. Weight is a force, and that we still use Newton's second law. So force equals mass times acceleration. The specific type of force is weight, and the specific type of acceleration is gravity. So we have W, which is the force, M, which is mass, G, which is gravity, which is the acceleration. If I plug in his value for mass, which is 100 kilograms, and I plug in acceleration due to gravity, which we use 10 for this. So 100 times 10. The units do not cancel. So Newton is actually a derived unit of kilograms meters per second squared. So Newton is the same thing as kilogram times meter over second squared, because these units do not cancel. So it is a derived unit, Newton. So 1,000 newtons. So his weight will not change the whole time. If you look at the diagram, if you look at the picture, for all positions, so position A, B, C, D, E, and F, his weight is 1,000 newtons. Right. For each section, I went ahead and boxed it so that it's easy to see what numbers go together. So this is A, B, C, D, E, and F. Starting with A, we want to first, before we can figure out if we're accelerating or what the acceleration is, we need to know the net force. So net force is the total force added together. We're going to call downward positive and upward negative per the instructions listed. So it does say to let downward be the positive direction. So we have positive W, and we are subtracting resistance. So net force equals W minus R. So for A will be 1,000 minus 0. So the net force for A will be 1,000 newtons. So that's a net force. For B, the net force will be 1,000 minus 400. So 600 newtons. Net force for C will be 1,000 minus 1,000, so 0 newtons. D will be negative 200. For E will be negative 1,000. So we do, remember we're doing weight minus resistance, so 1,000 minus 2,000. And then our final is 1,000 minus 1,000, so 0 newtons. So now we're going to calculate the acceleration for each position. Acceleration is net force over mass. It's a rearrangement of F equals m times A. So I have rewritten that formula here. It's also in the image right here. So it's also right here. We have acceleration is net force over mass. And I have that here as well. So for each position now, we're going to calculate the acceleration using the net force that we calculated in the last step and dividing by the mass of the man, which was 100 kilograms. So I don't have the units typed in, but it would be 1,000 newtons divided by 100 kilograms, which remembering that Newton is a derived unit, it cancels out the kilograms, and then you're left with meters per second squared for your unit, which is your acceleration. So 1,000 divided by 100 is the acceleration at this point. So we're going to type that in, and it's 10. So that is actually acceleration due to gravity. So before he has any air resistance, he's getting a maximum acceleration of 10. Then we go down to the next box where he has started to fall, and he has some air resistance, but the air resistance is still less than the weight. So acceleration would be equal to 600 newtons divided by 100 kilograms, and that would give us an acceleration of 6. So less than gravity now. In our next one, we have net force is 0. So we have A equals 0 divided by 100, which would be 0. So no acceleration. There's a fancy name for this particular scenario, and that is terminal velocity. So terminal velocity occurs when the falling object is no longer accelerating, and that would be the situation right here. So when the air resistance is equal to the weight, you get a net force of 0, which means your acceleration is actually 0. So when you first start falling, in normal falling, you have an acceleration of gravity. But as you start to move, as air resistance starts to cancel out your weight, your acceleration drops to 0. So something that is at terminal velocity is still falling. So he's still falling. He jumped out of a plane and he's falling. But when he stops accelerating, so he's not speeding up anymore, he's at terminal velocity. And that's the end point of his velocity. That's the fastest he can fall. And he'll continue at that velocity unless conditions change, meaning that unless the air resistance changes, the surface, something changes regarding how he's experiencing air resistance, that's the only thing that can actually change it. All right, so keep on going here. So then we have the next one. We have acceleration equals negative 200 divided by 100. So that would give us an acceleration of negative 2. So -2 actually means that you're slowing down. So we're referring to, in this example, we're using positive to indicate downward. So we have a downward acceleration of 10, then 6, then 0. Once the parachute starts to open, though, it changes his surface area. So he's increasing his surface area, which means that now he's experiencing more air resistance than he was in the previous box. So up here at terminal velocity, he was experiencing an air resistance of 1,000 newtons, which is equal and opposite to his weight. But once his parachute started to open, it increased his surface area, which increased the air resistance. So now he's experiencing a negative acceleration, which means that he's actually slowing down. So his velocity is now changing at this point. Going ahead and moving down to the last two calculations here, we have acceleration equals negative 1, oops, 1, 2, 3, negative 1,000 divided by 100, which is equal to negative 10. And then last we have acceleration equals 0 divided by 100, which is just 0. Okay, so now we have a net force of 0 again, which means we're no longer accelerating, which means that we're at that special place called terminal velocity again. It's a different terminal velocity than before, which is kind of how parachutes work, right? When you're falling without a parachute, you're falling way too fast to hit the ground safely. But with a parachute, it increases your surface area. So he had the parachute with him the whole time, so his weight didn't change. He's still 1,000 newtons, but he's able to fall slower because he's increased his surface area, which means that he must go slower for the weight and air resistance to be equal. And so he's able to stop accelerating, reach terminal velocity again, and fall at a safe velocity that he can actually land alive, right? All right, the last step is going to be to answer the questions, the multiple response questions. Number one, when Bronco's speed is least, his acceleration is which? So when you fall out of a plane, you're going slowest when you're not moving. So at the very beginning, before he starts to fall, that would be the slowest he's going. And it's also when he has maximum downward acceleration. So when his speed is the lowest, his acceleration is the most. Number two, in which position does he experience downward acceleration? So we're referring to positive is the downward direction. So let me go ahead and mark that for you. So it says letting the downward be positive. So whenever the acceleration is positive is when we have a downward. So in which positions is there a downward acceleration? There are 2 points where there is a positive acceleration. So you can identify those by looking at these calculations we did. Number three, in which position or positions does Bronco experience an upward acceleration? So since we've defined downward as positive, then upward would be negative. So you're going to identify in which positions the acceleration is negative, and there are 2 positions that meet that criteria. Number four, when Bronco experiences an upward acceleration, so that would be positive in this, negative in this case, his velocity is still downward or upward also. So when someone is falling, they're always falling down. So unless they have some sort of an engine to push them upward, they are still falling downward the whole time. that experience or that look of someone skydiving and it looks like they go up when they open their parachute is only from the relative perspective of another skydiver. So if you have two skydivers falling together and then suddenly one opens their parachute, they slow down, and the person that did not open their parachute did not slow down. And so it looks like they went up when in fact they're just going slower. It's like if you were two cars driving on the freeway next to each other going 65, and one person suddenly brakes. They're still driving forward. They didn't start going backward, but they're just going slower. So, from your perspective in the faster car, it looks like they went back. But from an observer on the ground, they can see both cars still heading in the same direction, just one is now going slower. And the same thing is happening with skydiving. You have two people skydiving coming down like this, and then one person opens a parachute. They're both still falling, but this one is just starts to fall slower. So it looks to this perspective like they went up, but it isn't really the case. This person is just still falling fast, and this person is now falling less fast. Question 5. In which positions is Bronco's velocity constant? So, by definition, when velocity is constant, acceleration is 0. And so any place where the acceleration is 0 is when the velocity is constant. In which positions does Bronco experience terminal velocity? Terminal velocity is maximum velocity, which also means 0 acceleration. Number 7, in which position is terminal velocity the greatest? So there's 2 times whenever he has terminal velocity, and it's asking which one is he going the fastest. So is his terminal velocity faster when he's falling with his parachute closed, or is he falling faster when his parachute is open? If Bronco were heavier, his terminal velocity would be greater, less, or the same. So if he were heavier, the number that would change would be the weight number. So the W would be a bigger number. What this means is that when he is falling and he reaches whatever this velocity is at position C, he won't be at terminal velocity yet because the weight will still be bigger than 1,000. So as he's falling, his air resistance is the result of his velocity and his surface area. So he goes from 0 to 400 to 1,000, and there's some speed that he's falling at. But if he were heavier, he would still be speeding up because the net force wouldn't be 0 yet. The air resistance and velocity at this moment would be the same, but his weight would be greater. Therefore, he would still be accelerating. And so you would have, if you had 2 skydivers falling at the same time with the same parachute, and one was heavier, the heavier guy would fall at a faster terminal velocity and reach the ground sooner than the lighter parachuter.